All right, guys. It's gonna be a short video where I want to introduce the second of three special cases in Chapter 6. We mentioned the first special case was sliding friction, which we've dealt with, I think, in some detail. And the second case is centripetal forces, and then that will leave us with only the third case, which are drag forces remaining. So let's take a look at this special case of centripetal forces. So maybe a good place to start is we could imagine an object moving in a circle. So let's say I've got a circle here, and we'll imagine that this is, some sort of perfect circle. And maybe what this could be is a top-down view of me. Say that's me in the middle, top-down view. My shoulders, here's my arm, my hand. And I'm holding here a string, and on the end of the string is some mass, some object here, some object. We'll say that object has mass m, and maybe we can say that the radius of the circle here, which would be like this distance, the radius of the circle, we'll call that r. And let's imagine I swing this thing in the counterclockwise direction. So this particular object has a velocity v. And there we go. So first thing we might notice here is that this object, as we've discussed before, is accelerating. There is an acceleration. Specifically, there is what we call a centripetal acceleration. And that's due to the fact that the object is turning. So since we have circular motion, that means that there is an acceleration. This is called a centripetal acceleration. We already know this. That acceleration, a sub c, you'll remember, is equal to v squared divided by r. So that's just a quick reminder of our centripetal acceleration, v squared over r. And the units there, as always, are just meters per second squared. So that's something we already knew. But now something we know, since we know about Newton's laws, we know that acceleration has to be caused by a force. And that gets us to what centripetal forces are. Centripetal forces are just forces that produce circular motion, that produce and or maintain circular motion. So I'll put that here. These are forces that produce / maintain circular motion. In other words, if we think about this mass on the end of the string, it will continue to move in a circle so long as there is some force causing it to move in the circle. Now, in this case, I don't think it's too mysterious what the force is that's causing circular motion. I think it's pretty clear that we're going to have a force inward this way, which is the tension force. There's a tension force here, T, from the rope. And that's the force that's causing the mass on the end of the string. That's what's causing it to move in a circle. I'll note that this tension force is indeed pulling inward on the mass. The rope pulls in on the mass towards the center. And just as a reminder that that's what centripetal means. Centripetal means center seeking, or in towards the center. And this is indeed a center-seeking force in the sense that the direction here of this vector arrow, that direction is in towards the center of the circle, which is like my head. So again, not mysterious in this case what that centripetal force is. It is the tension force. In other words, if I drew an FBD of the object, that mass, if I drew a free body diagram of it, top-down view, the only force here that's acting is, again, that inward force of tension. So in other words, the tension force here is the net force. So I could say this if I wanted to. I could say the tension force is F net, since there are no other forces. And maybe I'll just mention very, very briefly, sometimes there's a temptation here. Students have to think that there should be some outward force. Sometimes some students want to draw an arrow this way because they think, oh, well, it feels in my hand like that mass is trying to come flying out of my hand. So they think, oh, there's got to be some kind of an outward force. And sometimes they even give it a name. They call it a centrifugal force. Centrifugal force. These centrifugal forces are bogus. They don't exist. There is no outward force. This is a common misconception. In fact, if you hear people talk about centrifugal forces, they're probably talking about something that doesn't exist. So that was all a digression to say that there is no other force acting here other than the tension force. So the tension force is the net force, which means that the tension force here is equal to ma. And we know what a is, right? We already noted that the acceleration is this. This is the centripetal acceleration. So now I can say in this case that the tension force is equal to m times v squared over r. And now we have an equation for centripetal force. This thing right here, this is our centripetal force equation. So this isn't really a proof, it's sort of more of an argument, but now I can say that centripetal forces in general are equal to m times v squared over r. These are centripetal forces. This is how we calculate all centripetal force. And the unit here, of course, is the Newton, as all forces are. So you might be thinking, oh, well, this is really, really quite simple. It can get a little bit trickier because I want to point out this argument I made up here, and you might have wondered why I made it. This argument up here about the tension force being the net force. It turns out the centripetal force is a net force, and that's a very important little warning to give. The centripetal force is a net force that acts inward, that acts radially, meaning along the radius, radially inward. And there are some cases where there are multiple forces that contribute to this net force. In this case, there was only one force, it was tension. But in some cases, there could be multiple forces. And I'll get to that in a minute. But before I get to that notion, I just want to point out that sometimes it can be actually kind of hard to identify what the centripetal force is. So let me give maybe just one other example where you might have circular motion and it's not necessarily super obvious what the object is that's moving in a circle. All right, how do I do this? Okay, let's try this. So here is a circle, and maybe what I've got in this case is a car. So let's say this is a top-down view, and here's a car, top-down view. There it is. I have no idea how to draw a car. And there are the wheels. You're looking top-down. There's the muffler. And so the car is moving in this direction. That's the direction of the velocity. Here's the center of the circle. So this could be like, if you like a traffic circle or a rotary, whatever you call it. Cars moving in a circle. And so you might well wonder, what is the force that's causing circular motion? How is the car staying in a circle? And it might not be immediately obvious until you think about under what circumstances would you try to go in a circle and the car wouldn't be able to? And you might be able to say, oh, well, maybe the road is icy or snowy. And maybe I couldn't make the turn because of that. And you'd be right, because the thing that does maintain friction in this case maintain circular motion is friction. So in this case, the friction, it is a friction force that maintains circular motion. So the centripetal force here, in this case, the centripetal force is a friction force. And it's actually, this might surprise you, it's a static friction force. It's a static friction force because even though the car is moving, the car is not, or better not be moving along the radius. It isn't moving in the direction of the radius. It's only moving tangent to the circle. So we consider it a static friction force. So that's another example. There are other examples of centripetal forces. Normal forces can be centripetal. Gravity is often a centripetal force. There are lots of different examples of centripetal forces. But I promised to give you an example of pointing out a case where maybe the centripetal force is a net force. So let's go back to the very first example we had, where we had a mass on the end of a string. But what I want to do now is imagine that rather than the circle being a horizontal circle, in other words, rather than a top-down view, let's imagine that this is a view from the side. All right, so here's a string. And on the end of that rope or string is a mass, again, just like we had before. Here's that mass. But I want to imagine that this is a vertical circle, meaning that this is a vertical plane. And again, we're going to have the same idea. Here's mass M. We're going to say that the radius of the circle is R, right? This radius right here. This is R. And again, we're going to imagine that this object is moving with a constant velocity v, just like before. But since it's a vertical circle now, we've got to be a little bit careful. So for instance, let's imagine the following case. Let's imagine the case down here. We'll call this position A. If I think about the mass when it's at position A, if I drew a free body diagram here, FBD, for position A, what I would notice here is if that's the mass at position A, right, we're right there, then I would say there are actually two forces here. I've got gravity acting downward, mg, and I've got the tension force acting upward. And at first glance, you might say, oh, well, maybe they're just equal. You should hopefully notice they cannot be equal. The tension force has to be bigger because there needs to be a net force in this direction. There has to be a net force towards the center of the circle. There's got to be a net force this way, which we call the centripetal force. So that net force inward is the centripetal force mv squared over r. So now what I would say is T minus mg equals m times v squared over r. The difference between these forces, the net force, has to be the centripetal force. So again, this right here, this is F net, and this is the centripetal force ma. So here I would say the tension force is equal to mg plus mv squared over r. Now let's think about this point up here, which I could call point B. And now let's do the same exact line of reasoning for point B. Here's a free body diagram at point B. What are the forces? Well, now there are two forces and they are both down. Gravity is acting downward as always, and the tension force is also acting downward. When the object's at this point, the tension force is pulling inward and gravity is pulling inward as well. So there are two downward forces. So again, I'm going to say F net equals ma, mg plus t equals m times v squared over r, right? There's a centripetal acceleration. A is v squared over r. So in this case, I would say t equals mv squared over r minus mg. And now I just want to compare this result that we just got with this result down here. And if we compare these two, what we notice, hopefully not to our surprise, is that the tension force at the top is going to be less than the tension force at the bottom. In other words, T at point A is going to be greater than T at point B, right? This is T at point A, and this is T at point B, and T at point A, there's a plus sign here. T at point B, there's a minus sign. So TA is bigger than TB, which I think is intuitively clear. If you were to imagine swinging this mass on the end of a string, you could sort of feel that the tension force is greater at the bottom than it is at the top. And now we know why, and it's because the centripetal force requirement, mv squared over r, is equal to the net force, which in this case is the combination of T and mg. So that's a very, very quick, brief introduction to centripetal forces. You're going to have a chance to practice these techniques and looking at a variety of different situations on the problem set.